we have perceived model, preconceived model. We want to see whether there's a good fit to the sample data with a preconceived model. For example, if you have assume you have an underlying random variable x. Obviously, if you have a random variable, you will have samples or realizations. And you just draw random samples out of this random distribution. Then what you are going to have is x1, x2 to xn. So if you get this data, so this is what we call data. Then one graphical tool we can use is the histogram. So let's see, we might have a histogram look like this. Okay, we might also have a histogram look like this. And then you might see, oh, this is a histogram. And I see there's a shape. So this is my preconceived model. So what I'm saying is the line could be the preconceived model. You might say, oh, maybe this is from the normal distribution. Okay, maybe this is from the exponential distribution. So we want to check whether there is a good fit with a particular model. So this is called chi-square goodness of fit test. Now, if we have the data, the first step will be construct a histogram with m bins. Okay, so the bins will be bj, and then j equals to 1 to m. So this will be the b1, and then we have b2, b3, b4 to, if we have a bin here, this will be the bin m. So those are all the bins you have. So this is b1, b2, and then you have all the way to bm. So those are the bins. Now, the next step is the estimate the probability Pj of Bj. That is the J spin. Okay. So what is Pj hat? Pj hat is the estimation from the data. So if we want to estimate, for example, Bj right here, and then what's the probability to fall into Bj? That is Pj hat. This will equals to Nj. What is Nj? Nj is the number of observations in the J spin divided by total N. Total is the total number of data points we have. So Pj hat will equals to Nj over N, and J equals to 1 to M. What is Nj? Nj is number of observations in the J spin N is the total number of observations. You can also call it number of data points fall into this bin, this particular bin. Okay, how many data points we have. This is a relative frequency we discussed before for when we construct the histogram. Now the next one is if you have the model, if you calculate the probability from the model, that is a PJ. That means this line is like the population, and those bars are like the sample. So you have sample estimation. That's PJ hat. We also have preconceived candidate model. So preconceived candidate model means after we check the histogram, we might have some ideas in our mind that, oh, this might be the normal distribution. This might be the exponential distribution. Now, if we assume this is from exponential distribution, now let's see what is the probability. Obviously, if we have the preconceived model, we will have f, x. So we have parameters theta. This is CDF function. We also have PDF function. This is x given theta. This is a PDF function. Okay. So if you give this candidate model, obviously, if we want to get estimate, if we want to get a PJ, this will be probability that x belongs to the bin J, the J bin. So if we have the CDF function, this obviously equals to the upper bound of J given theta minus the lower bound of J given theta. And also J equals to 1 to M. So those are this is a preconceived model. So now, obviously this PJ and this PJ hat, they will have discrepancy. But if you have a good model, these two will be very close to each other. So this is called a good fit. Now, let's see how can we. Now, let's get into the goodness of fit test. First, we want to have the OJ. OJ is the number of observations in BJ. So this will equals to PJ hat times N. And expected observation. This is the number of expected observations in BJ. This will equals to PJ times N. So this is expected. And this is what you observe. Okay. Now, we will get a test statistic, which is called S squared. This will equals to summation J equals to 1 to M OJ minus EJ divided by EJ. Okay, square. And obviously, this is the expected observation. It's greater than 0. And this is a square. So those are the difference between what you have observed, what do you expect there to happen, okay, in bin J. So this is greater than 0. So if you have a good fit, what will happen for a good fit? What will happen for a good fit? Then S squared will goes to very small. That means smaller and smaller. That means OJ is very close to EJ. That means you have a very good fit. And here, S squared is a realization. It's a realization of chi-square K random variable. Okay. Now, what is K? K is the degree of freedom. That is DOF. And K equals to M minus theta minus 1. So what is M? M is the number of beings. What is theta? Theta is the number of parameters. In the preconceived model. Okay. So if you have a normal distribution, how many parameters you have? So if you have a normal distribution, this is fx theta and capital Fx theta. So normal distribution has two parameters. That is mu and sigma square. So two parameters, mu and sigma. And however, for exponential, you only have one parameter, that is lambda. Okay, now let's get back. We're going to define p-value of chi-square. I'm going to use the goodness of fit test. This is goodness of fit. So this is a probability if we have a chi-square k greater than s squared, that is our p-value. Okay. Again, let me reiterate, the smaller the p-value is, the stronger evidence against the null hypothesis. The stronger evidence against the preconceived model. So why is it smaller? Because if you look at a chi-square distribution, this is a chi-square, and this is a chi-square. So if s squared is right here, this will be my probability chi-square k greater than s squared. So if this area is very small, okay, if this area is very small, okay, then the s squared should be very far away from 0. S squared will getting bigger. So what s squared, but s squared is actually equals to you see here, S squared equals to OJ minus EJ. So S squared equals to summation J from 1 to M, OJ minus EJ squared divided by EJ. You see, if this one is getting bigger, that means OJ and it's very much different, has big difference, is different from EJ. So if OJ is far away from EJ, that means S squared is bigger. S squared bigger means p-value is smaller. P-value smaller means that the preconceived model is not right. That is because OJ, you expected observation is very much different from what you have observed. Okay. Now, p-value, how to use the p-value. We are going to compare p-value with significant level. Significant level alpha. And you can say we're going to reject preconceived model. If p-value less than 0.05. So this is our commonly used model, significant level. You can also use 0.01 if you want to be pretty rigor or give a very strict criteria, or you can relax, give 0.1. So this is very similar to what we did in the hypothesis testing, but this is a p-value approach. Now we have a few rule of thumbs when we do this test. The first question is how many bins? Because when we do the histogram, we often have a question, how many bins do we use? So rule of thumb for number of bins. This is for the histogram. Okay. If you have sample size, number of bins actually depends on the sample size you have. Sample size n and number of bins. If your sample size is like 20, sometimes you don't use chi-square test. If it is 50, you use 5 to 10 bins. If it's 100, you use 10 to 20 bins. If it's greater than 100, you use square root of n. This is the number of bins you're going to use. Okay. And you're going to have expected observation. So EJ, rule of thumb for the size of EJ. What is EJ? EJ is expected number of observations. Note, the chi-square goodness of fit test is not valid if EJ is too small. There is no general agreement on the minimum expected EJ allowed, it is suggested that EJ greater than 3, 4, or 5. I mean, you better have more than 3 observations in a bin. So what if you have a bin that is only have 1? Then what do we do? If an expected EJ is too small, then 2 or more bins. When we say 2 or more bins, they are adjacent. That means they are neighbors next to each other. You can merge them together so that they can be combined. So this gives us the theoretical part of the chi-square goodness of fit test. Now, let's have a look at an example on chi-square goodness of fit test. Now, let me put a cursor here. I can put a cursor here. Now let me insert the exercise here. Just 1 second, it will come out. Okay, done. Now let's go back to the first page. Okay, so this is a in-class exercise, but let's look at this exercise together. So we have a lifetime light bulb company. They want to guarantee their product for 10 years of the operations. Okay, so then the quality engineer come out with an experimental plan. They stress the light bulbs and use higher than normal voltage, which can simulate 1 month of typical use by a customer in 1 hour of laboratory testing. So a random sample of 100 bulbs, okay, we're gonna do a random sample of 100 bulbs, record the equivalent typical user months failure for each light bulb. So this is the data we got. So we want to check out the lifetime of the light bulb, whether they actually, the exponential distribution is a good fit. So far, if you want to find out whether you have good fit to, let me zoom in a little bit. So you see here, once you got the data, no matter it's from light bulbs or from any data set, you can do the histogram, no matter what the distribution is. Then from the histogram, you can visually, this is a graph, right? So you can visually make just a preconceived model. You said, okay, this is from a normal model. For example, this one here. This is a normal distribution. This is exponential distribution. Then you can test this hypothesis. So chi-square goodness of test, obviously the graphical method is based on the visual judgment. However, chi-square goodness of fit is a very quantitative method. You actually trying to do the hypothesis testing to see whether your preconceived model is right or not. Now let's look at this again. So this is the data we got. Let's look at this data. So this is 1 month. The second, this is the first month, we have 1 failure. Okay, record the equivalent typical user months of failure. So this is month 1, we have 1 failure. Month 2, we have 2 failures. Month 3, we have 1 failure. And then this is month 889, we have another failure. So those are the, you see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is 10. And this is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So in total, we have 100 light bulbs. Each value is the lifetime of the light bulb. So this one failed at the month 4. This one failed at month 52. So after we got this data, the first step is to construct a histogram. Let's construct a histogram. So before we construct the histogram, please note, because the last data point, this one, let me change it to a different color. Because this data point is actually far away from the rest. You see, this is 1, 2, 3, 4, 5. They are very close. You see, 522, 547 is about 25, right? The laboring distance is about 25, but 547 to 889, the distance is about 300, and more than 300. So in this case, we are going to get rid of the outliers. So because the last point is far away from other points, we ignore the last point and use 547 minus 1. We just, when we construct the histogram, we only use this range because this outlier can be combined to the last bin of the histogram. But when we do the range, we don't want something that is very far away from the other data points. So this is a range, the 547, and this is 1. So we use 547 minus 1, this is 546. We use this as the actual range. Then now 100 points, the rule of thumb is like we take 10. Square root of 100 is 10. So we use 546 over 10. This is 554.6. And we're going to use 55 as a bin width. Now let's make the bins. So 0 to 55, 55 to 110. Then we put the number of failures, how many of them fail between 0 to 55. 55, this is 40. 40 is about here, right? So this group is actually from 0 to 55. Obviously, we included 55 over here. Okay, so this is this range. We have how many failures we have? We have 40 failures. Okay, 40 observations. Or you can say 40 observed failures in this range. So this is 40. And now we're going to use 55 to 110. And then you got 23, 110, where is 110? Right here. And then 110 to 165. 165 is right here. And then 165 to 220 right here. And that's 10. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And then we can keep going. And then greater than 540. Greater than 540, we only have one, this guy. So this is our outlier because EJ is too small. We want EJ to be greater than 3, 4, and 5. So if this is too small, then we can combine these three together as one bin, okay? And let's see how did we do the combination in the next slide. So once we haven't come to the combination of the bins yet, let's first use this kind of observed samples in each bin. Let's construct the histogram first. So step 3, we are going to graph the histogram. By comparing the shape of the histogram to the exponential PDF shape, we hypothesize hypothesized that an exponential model may be a reasonable choice for the data. Okay. Okay, so this is our histogram. So we have 40. Now, if we want to calculate the probability in this region, so this is our exponential. Maybe this is our exponential model. Now this is our observed. We have OJ, and we also have this is OJ. And we also need to calculate EJ, okay? So in order to get EJ, we needed a total number of observations times PJ, okay? Since that I have a times PJ, because OJ equals the total number of the observations times PJ hat. And this is N equals to 100. So if we want to get the PJ, we need to get the model. Now, step 4, let's get the preconceived models. Test whether the exponential distribution is the lambda is a good fit to the data. So how do we get the lambda? This is a mean time to failure. Lambda, mean time to failure equals to 1 over lambda. And then lambda equals to 1 over mean time to failure. Okay, so now we need to calculate the average failure time. So you just sum all the failure time together, you will get the mean time to failure. Then you will get the lambda. This is 0.0074. So we assume this is our model and lambda equals to this one. Then if we want to get the PJ will equals to the F upper bound J given theta minus F lower bound the being J given theta. Okay. So we can do that. Now let's do this. The chi-square goodness of fit is not valid if the expected frequency are too small. There's no general agreement on the minimum expected frequency allowed, but the values 3, 4, or 5 are often used. So if an expected frequency is too small, 2 or more bins, you can say this is bins or classes, can be combined. So here, what did we combine? We combine this 3 and 4 together, and we combine this group also together. Okay. So now let's see how do we get the upper bound minus the lower bound. So the upper bound minus the lower bound, for example, this is the actual failures. So this is interval. This is my observed failures. This is my expected failures. This is my PJ. So how do we get it 0.334? We're going to use the upper bound, 55, minus the lower bound, upper bound minus lower bound. So this is a CDF function. We know the lambda is actually 0.0074. Then we got this probability, this PJ over here. And then this is actually equals to 100 times PJ equals to 100 times 0.334. So we got this one. Now this is and then we can do this for all of them. And then we will be able to get all the expected failures. Okay. So this, if we combine this group together, this will be 8, this will be 7. But what we expect over here will be 4.4, 2.9. This is 7.3, okay? And this group, if we add them together, this will be 92976, right? So this will be 5.8. Now we have OJ, EJ. Now next is to calculate the S square. S square equals to J from 1 to M, OJ minus EJ. And the M is the number of bins you have. How many bins you have? This is bin 1, bin 2, bin 3, bin 4, bin 5. And then we combine this together. This is bin 6, and this is bin 7. So in total, we have six bins, okay? So this will be the first bin is 40 minus 300, not 300, it's 33.4, okay? And then the second bin is 23 minus 22.3. And then we have this is the bin 1, this is bin 2, bin 3, bin 4, bin 5, bin 6, bin 7, okay? So this will be the first bin interval, second bin, third bin, fourth bin, fifth bin, sixth bin, and a seventh bin. Okay. So in this way, we are able to get 6.3. So 6.3 is our value here. And the degree of freedom, we have one parameter, right? And we have 7 bins and minus 1. So this is K definition. So we got a 5. Now we are going to get the p-value. P-value equals to chi square K degree of freedom greater than S square equals to 1 minus, right? So this is our, if our S square is here, so this part will be our p-value, okay? And we can, okay. This is a critical value approach. This is a classical approach. This is a p-value approach. In the classical approach, if you observe S square over here, which is greater than the critical value, then this is my rejection region. This is an acceptance region. If you S square is here, then you accept. But if you S square is right here, we're going to calculate this p-value. And then we compare this p-value is greater than or less than the significant level. Alpha. So how to get this p-value? The p-value, if you use Excel, is 1 minus chi-square distribution, because in Excel this is the lower tailed. CDF function is lower tailed, and so that's why we need to get the 1 minus. So the p-value is actually 0.2781. 2781 means we are actually the smaller than we reject. If this guy is smaller than 0.05, then we reject, or 0.01 we reject. But now it is pretty big, right? So we don't reject, and we think that the exponential distribution is a good distribution for our, is a good model for our data. So the chi-square goodness of fit does not have to be limited to the exponential distribution. It can be used for normal distribution. It can be used for gamma distribution or variable distribution. Any distribution you can think, and no, as long as you hypothesis, you have a hypothesis that you preconceive the model is a particular distribution, then you can draw the histogram and then fit the model and try to fit the model. Okay, so this is chi-square goodness of fit test.